So in this model, we will represent the two 2s orbitals on the two oxygen atoms as spheres. So let's imagine they're the same as these red spheres in my model. We walk through each operation and indicate how many orbitals stay in the same places. So identity operation, pick it up, put it back down. 2 orbitals stay in the same places, we write down 2. Rotation around the z-axis. This is the z-axis because it's the axis of highest order rotation. If we rotate around that axis, we see that the 2 orbitals stay in the same place, so we write down 2. If we rotate around the x-axis, we've defined that as being up and down. If we rotate around this axis, 2 orbitals move. So we write down 0 because 0 orbitals have stayed in the same place. If we rotate around the y-axis, that's coming in and out of the screen. Rotate around the y-axis. 2 orbitals have moved. 0 has stayed the same, so we write down 0. For inversion, that's a little bit harder to show. This orbital goes through the center and comes out on this side. This orbital goes through the center and comes out on this side. 2 orbitals have moved, 0 stay the same, we write down 0. For reflection through the XY plane, remember x is up and down, y is coming out toward us. The XY plane is like this, sort of coming in and out of the screen. So if we reflect through the XY plane, this orbital and this orbital change places. 0 has stayed the same, we write down 0. The XZ plane, X, Z, is the plane of the screen. If we reflect through the plane of the screen, that's the plane of the molecule, then 0 orbitals will move, 2 will stay the same, we write down 2. If we reflect through the YZ plane, Y is coming toward you, Z is the axis of highest rotation, so that's this plane, coming flat through the molecule. If we reflect through that plane, then these 2 orbitals will stay in the same place, so we'll write down 2. Here are my PZ orbitals. So Z is the axis of highest rotation. Let's do each of the operations. If we do the identity operation, both orbitals have stayed the same. We write down 2. If we rotate around the z-axis, both p orbitals have stayed in the same place. This one on this atom, this one on this atom. So we write down 2. If we rotate around the x-axis, x is going up and down, rotate around x, both orbitals have moved. This orbital went over here, this one went over here. So we write down 0. Rotation around the y-axis, coming in and out of the screen at you. Both orbitals have moved, so we write down 0. Inversion, this atom comes over here, this atom comes over here. Both have moved, we write down 0. Reflection through the XY plane. So XY plane, here's the plane. If we reflect through that plane, we see that these 2 will change places, so we write down 0. Next, reflection through the XZ plane. So we said X is this way, Z is this way. This is the plane of the screen. If we reflect through the plane of the screen, the mirror plane cuts through the atoms. So neither of the orbitals moves. We write down 2. And then reflection through the YZ plane. So Y is coming in and out at us. Z is this way. The YZ plane also cuts through the orbitals. So neither orbital moves. We write down 2. Here's my set of 2px orbitals. If I pick them up and put them back down, then the identity operation, then both of them stay in the same place. So I write down 2. If I do rotation around the z-axis, I see that my orbitals stay in the same place, but importantly, the sign of the wave function changes. So see, it's unshaded up here, and if I rotate around the z-axis, now the shaded part is up. So since the direction has reversed, but the atoms have stayed in the same place, the orbitals are in the same spots, we write that down as a -2. So -2 in the z-axis rotation. If we do C2 around the y-axis, that's coming in and out of the screen, both atoms move, so we write down 0. And rotation around the x direction, up and down, both atoms move, we write down 0. Inversion, this atom changes places with this atom, so we write down 0. In reflection through the xy plane, xy plane, both orbitals move, so we write down 0. Reflection through the xz plane. Xz plane is the plane of the screen. It will cut through the molecule, and so, but it will keep the sign of the wave function the same. So this will be 2. Finally, if we reflect through the yz plane, so y is coming out at you, z is the axis of highest rotation, so that plane goes like this. And this will also cut through the molecule, so the orbitals will stay in the same place, but their signs will be reversed. This lobe will point this way, and this lobe will point this way. And so since the signs are reversed, that we'll write down in our reducible representation a -2. Here's our group of 2p orbitals, and you can see they're coming in and out of the screen toward you. So if we pick up the molecule and put it back down, we see that both orbitals stay in the same places and in the same direction, so we write down 2. If we rotate around the z direction, we see, so rotate around the z direction, we see that the orbitals stay on the same atom, but they reverse the sign, so we write down -2. If we rotate around the y direction, that's coming in and out of the screen, around the y direction, then we see that both orbitals move, so we write down 0. If we rotate around the x direction, that's up and down, we see that both orbitals move, and so we write down 0. If we invert to inversion center, so this atom becomes here and this atom becomes here, both orbitals move, we write down 0. If we reflect through the xy plane, so x, y, it's this plane, we see that both orbitals move, so we write down 0. If we reflect through the xz plane, so we said x, z, that's the plane of the screen, we see that the orbitals will stay in the same place, but their signs will reverse, so we'll write down -2. And finally, if we do the yz plane, so yz plane, we're going to cut through the orbitals, but in such a way that the sign stays the same. So we'll write down 2.